Hi, my name's Mark Randall. I'm Senior Project Officer with the Queensland Government here in Australia, and I'm going to talk to you about STIV analysis using Hydro-STIV software, using fixed cameras and drones. So in 2016 to 18, I ran a project looking to validate image velocimetry methods, looking at both LSPIV and STIV techniques. Now, at that time in 2016, there was only one STIV software available, which was Hydro-STIV. Now, it does get a little bit sort of confusing in terms of terminology because a lot of acronyms contain the IV part of things. But the main difference between STIV and other types of image velocimetry or LSPIV image velocimetry is that it doesn't use a cross-correlation methodology. So it uses a completely separate system to calculate the surface velocities. So eliminating that cross-correlation technique, we found for our conditions provided a much more robust analysis of the surface velocities for environmental conditions. So it seemed it handled glare and shadows a lot better than our LSPIV software. It fitted into a QC system because not being a cross-correlation technique, there was no need to worry about selecting frame rates that you were going to use, or images selected from the video that you were going to use, or search areas, interrogation areas. There was no filters. So with all of these sort of things removed, it made it a lot simpler for training and allowed a lot more sort of standard method for us because the STIV analysis didn't require changing the analysis lines, which I'll show you about in a minute, but those analysis lines were suitable for low and high flows. So after 2 years of validation, we adopted the STIV methodology. I should say that STIV was also developed by Professor Fujita, and at the time the Hydro-STIV software was the only available software for us to use for STIV analysis. So becoming a little bit more popular now, but as I mentioned, the STIV analysis doesn't use a cross-correlation, so it uses a gradient tensor method. So you set a number of search lines in the direction of flow. The analysis looks to track or place the changes in color intensity as tracer particles and waves structure move along the analysis search line, and as it does that with space and time, it creates a diagonal pattern like this, and the angle of that pattern then constitutes the actual velocity. So quite as simple as using all the frames within the video. Allows a lot higher resolution, so it's more robust for when tracer particles are few and far between or not equally dispersed. So the initial Hydro-STIV software was quite basic. It had only been out for 12 months when we started using it in 2016. Hydro-STIV took the original concept of Hydro-STIV and developed it a whole lot further. There's a couple of different packages for the Hydro-STIV. The advanced edition contains real-time processing, moving forward with the Hydro-STIV software has allowed us to greatly increase the number of videos that we can process. This is the standard software layout for the Hydro-STIV that we use. Consists of a number of windows. containing the various work areas that you progress through as you process a video. And the software contains a batch processing option. So after you've developed your initial file, you can process any number of videos from the same site. You just upload as many as you need to and then paste in the water levels, and that will just run automatically. So this again massively increased the amount of output that we can get from our imagery sites. The software contains a Google Earth output, which is excellent. Allows you to display your velocity analysis with a Google Earth map output, so it's great for sharing. As I mentioned, it contains the advanced edition contains a real-time STIV module, which will look to a cloud source location for camera videos and water level data, and then process those automatically as soon as they come in, and then process live results. There's some updates coming through at the moment for the next version of Hydro-STIV, and within that they're looking to now introduce water level measurements from either gauge boards or flat surface structures such as bridge piers. Other updates include image stabilization option, and also the ability to subsection videos. So, for example, a 1-minute video, you could select that a certain area and a certain length of time within that 1-minute video to process. This is just an example of one of our fixed sites. This is the ground control point layout for on the right, and any type of image velocimetry that you're going to use requires some sort of ortho rectification and some sort of scanning of the pixels. So the process, whether in STIV, is the same as an LSPIV software. The camera on the right there is just a fixed trail cam that we placed up in a tree. This was just a very quick setup. You can see there in the imagery cones laid out. We tend to use temporary ground control points and use this initial video to calibrate every other video. So it's a one-time process, one-time setup process within the software. We got the ground control point data, the XYZ, for this three-dimensional orthorectification from a photogrammetry model. So while installing the camera, we allowed the RTK drone to fly and build a digital elevation model, which we were then able to pull out cross sections and GCP information. This is an example of more fixed sites. So on the left there's a gauging station with a camera mounted off the pole looking down into the river. The middle site is kind of an offset. The power and the comms for the camera are contained in the gauging station hut, and the camera is mounted offset from the hut looking down onto the river. The site on the right is again another sort of individual independent setup. So the camera is on a 6-meter pole. Within the hut there is a logger with a water level sensor, communications, and this logger actually had a real-time or on-site processing module in there running the STIV. So yeah, we were able to have the videos processed on site. So this is again the ground control point layout for this video. This is just the near bank. Again, looking down, you can see our temporary ground control points laid out on the near bank, and there's some same on the far bank. And again, you place these within the elevation, the Z values of what you want to measure correctly. So you calibrate it for the whole stage range. And again, this is a one-time process. The data that site collected is what I'll be showing you with the software, but with the on-site processing, you can see here we had a couple of events within 12 days, ranging from 2 to just below 11 meters. The on-site processing from the camera using the STIV gave us a really nice loop rating, and lined up very nice with what actual measurements we had with ADCPs. You can see predominantly on the falling limb. You might notice as well these little clusters here. This is in relation, if you look at the hydrographs here, so where we've got it's not rising or falling, but sort of hanging around a certain gauge height. That's where we get these little sort of clusters of measurements, just with a little variation of discharges. Same here, you can see just over the 5 meters mark. So represents that period of time here where it's just sort of rising and falling a little bit, but not the significant rises as the flood events comes through, the rises and falls. So those type of scenarios where the stage is changing very quickly, we get this real nice consistent discharge, stage discharge relationship being shown. We also use a lot of drones. Predominantly a lot of our measurements are done using drones because each vehicle has one. Drones provide a mobile solution to collecting videos for image analysis. So whereas your fixed camera is waiting for a flood to come through, with a drone in your vehicle you can actually go to the flood and grab a measurement if you've got access. So provides a means to measure flows that if staff aren't happy to get in and use a boat with an ADCP, so obviously that workplace health and safety aspect to our monitoring as well. And again, the great thing about drone videos is that they don't require a full survey, so they only require scaling of a known distance within the imagery. So we'll cover that in the software shortly, but again, that allows one person to collect flood event video very quickly. You can use drones a bit like a fixed camera to collect an oblique view, and because you're collecting just at a single water level event, you only need 4 ground control points with an XY coordinates. So what we tend to do for this example, on the near bank, we'll measure out a couple of points of a known distance here. We use a rangefinder to shoot across at 90 degrees to the flow and get a distance across there. So same on this side. So we measure some distances, you can get a triangulation, and you can build some very easily build full XY coordinates to calibrate that imagery. That methodology is particularly handy for very large flows. This river is 450 meters wide, so we wouldn't lawfully be able to fly the drone and look directly down onto the river, it'd be too high. So using oblique view with that camera, and then using the same methodology that I just described would enable you to calibrate that imagery and get some velocity and discharge information from it. Just move on to the software. So I'm just going to show you the software now. So this is the Hydro-STIV software. This is our information regarding our video. So that's our video file there that we've loaded, the information regarding time frame, resolution, and number of frames per second. The software contains a number of different views. So with a fixed camera, we use the oblique shooting mode here, and we have the choice of the 2 different types of rectification. So the 3-dimensional XYZ perspective projection calibration, which is what we've got happening here, or the homography transform, which is the 4 points that I just showed you about with the drone. The software also allows you to do PTV analysis as well as STIV. With PTV, it will track or manually track floats or debris objects as they travel down the river to get their velocities and discharge. The software also has 3 different modes. So we have the normal cross-section data mode, which provides discharge and velocities. You have the survey line mode, which doesn't require bathymetry, but will give you the velocities along a search line. And then the manual mode is really sort of free mode. It allows you to place your STIV velocity search lines, any number in any direction and any location. So that's really good if you wanted to do an analysis along a reach with multiple lines or confluences, things like that. The software has a number of tabs that you work through, so as you complete the information required for each tab, it opens up the next tab so you can move to the next stage. So it doesn't let you progress unless you've actually completed each stage correctly. So if we move to our ground control point stage, so this was the imagery that I was showing you with our cones laid out. So yeah, they're not here in this imagery. We calibrate this in a previous video, initial setup video, and each time we get a new video, you can just load the new video into the software. All the calibration remains the same, so long as that camera hasn't been moved or zoomed. The calibration is fine, so you don't have to go through this process each time. Ground control point information is down here, so if we were setting this up, you can either load that information in if it's not there, or certainly load in your X, Y, and Z, your elevation data. If we were doing this for the first time, we'll be in this window here, and you've got the options up here to add a ground control point. You can move it or delete it. So if I was trying to pick out my cones, I would zoom into an area, find the point I wanted to mark, and add that in. So you would do that for each of your points. You notice as well that the window goes yellow, so that tells you that that's a working window. Once you've ticked to confirm the work that you've done, you can turn it back to green. So all the points are selected there. We've copied and pasted or loaded in the details for each one of those points. It's handy to draw a diagram or make a sketch noting which control point is each when you're setting this up initially. That now allows us to go to a geometric correction. So we select that tab. We would then enter our water level in here, and as I said, each time you would get a new video. This would be one of the changes that you'd have to make. So water level, we've got it entered in here, 3.536. We then execute our correction. It's given us some warning because some of those points exceed 2 meters. If we go back to our ground control points here, so now it's worked out the errors, reprojection errors for each one of those points. What the Hydro-STIV software does, you notice these green lines here dropping down. So they're another indication of the quality of your ortho rectification. Those lines should be nice and heading vertically down, and they're designed to sort of head down to where the water level is, or up to where the water level is when they're underwater. So that's, yeah, just gives you an idea of the quality of the rectification process. Once it's done that, it fills out the camera, or estimates the camera information as part of that ortho rectification. If you know this information already, then you can enter this manually. Adding fixed will lock those numbers into place. But essentially the software will look to estimate those from your ground control points. So once you've done that, if you move to the cross-sectional, I'll just go back. This is up here is the geometric correction window, so this is what that process produces. So this is where all the analysis takes place within this window, and essentially it looks like this because you think of your initial video over here, the same number of pixels are in the foreground as they are in the background, but obviously in the background here, this far bank, each one of those pixels has a larger on-ground size. So the pixel here could be, for example, represent 2 meters, whereas a pixel up here will represent, say, 20 centimeters, as an example. So that's why this image here is in this sort of cone-shaped. You can resize this image to get rid of areas that you don't need. So again, it's you click and drag your square. So I'm just going to drag this over the area that we're actually going to be working. Tick, so it's just zoomed into that area now. Okay, cross section. You can simply load your cross section here, so length and heights, chainage and depths. You can load that up in a CSV file. The software will then place that onto the imagery if you have known coordinates for the start and end points in relation to, again, to your ground control points. That will help. And also what you can do is either in this window, I don't want to use this window, I'm going to use our corrected image here. So by clicking on the left bank, you can click and set where it would go. It's pretty handy for drone measurements, as I'll show you, because you can try and actually get it to make sure it meets the water level. So I'll just reset that. And yeah, see how these both are yellow, so I need to accept the fact that I haven't made any changes. Now we've got our search lines started. So we can either manually set search lines here, so we can click draw them based on our lengths, just accept. So that's based on our size here, so using that method you could place more in a certain area than other areas. Again, the angle relates to, you want to set those up so the lines are with the flow. So we're just going to set this up now, for example, 10 meters, 25 lines. So we're just going to create that. Now these lines will go across the whole cross section because this one's set up to process various different heights. So as it comes up, the water will come up here into the bushes. So this, because it's automated, we've got this all set up to cover a range of heights. And the one nice thing about the Hydro-STIV software is you can play the video and make sure that your lines are lined up with the flow. As I said, if they're not, you can adjust that here, for example. If we change that to 50 degrees, create, so you can see it. It's now changed the angles of flow. So that just helps to line everything up nicely. With a fixed camera like this, it does make a difference if there's angle errors in there. So you try and set it up as nicely as possible. This is all the information over here in regards to the lines, the lengths, starting coordinates in real world and pixels, angles, etc. This option here is where you want the line placement, so you can either have it 50-50 on the cross-section line, or leading to it, or leading away. So that's just to help you set up in regards to any obstructions that you might have. We're just going to leave it normally. So once you've done that, you're then going to make your STIs. So that's going to create the image that I showed you about with the sloping angles. I usually use this this method down here for your maximum angle first. That's going to try and identify the most dominant angle within the analysis. So it's usually quicker. So you can see very quickly it's gone through all those 23 lines. We have our analyses on here. All these images are adjustable. You can change the text color, size of arrows, things like that. Again, on our oblique image here, as we go across, this has got noise in here, so it will be interpreting velocities where they shouldn't be, but they're not used in the calculation. If we wanted to remove those, we can just untick them here. And again, the same on the far bank. So we have a nice sort of cross-sectional printout with the velocities and discharges and the sections where it's been calculated. Over here and our results, you can can see it's got our calibration factor or surface alpha. We can either change that for all of those points, or we can click on individual ones and change them. So we'll just leave this set as that. The choice of calibration is mid section or mean section, so just like your weighting measurement basically. We do have some options to correct noticeable errors. So yeah, when a measurement is undertaken, our first thing is to check the velocity distribution. We look to see whether that looks realistic and suitable. If you wanted to go further, we can go on to the manual corrections. We'll ignore the first few lines because they're on the banks. Open this up. So this is our STI image. And as we move through those lines, you can start to see our angled patterns of the traces. The green lines represent what the analysis has done. So it's this particular analysis is looking for the dominant angle, which will be the faster velocities. And if we move further out, you can see as we move across the channel is approximately 300 meters from the camera. So you can see it's done an excellent job, really nice tracer patterns there. If we wanted to correct a mistake, we can look to manually define the angle. You can see up here it provides us with a velocity, and if you did multiple angles it would then average them. So you can define sort of, you can see variation sometimes within these lines for like pulsing and things like that, so you could average out velocity pulsing, or gravity waves is another one which provides a very distinct pattern for the peaks and troughs. If you choose to apply those, it will apply that velocity. It then brings up our red arrows. They replace. So they're going to show us now what the average is from those analyses. So if we remove the others, so based on the lines I've picked here, it's now picked out an average velocity from that information, and it's drawn their equivalent angle onto here. So in a quality management system, supervisors then able to come and check what has been done, and if they're happy with it, accept it. If not, they can correct it themselves or go back to the original analyses by resetting it. The way that you know that something has been changed or corrected manually is because those lines will go with red text. So again, part of a quality management system, we know what's been automated, we know what's been changed by the person processing the measurement. We also have a different option for difficult analyses or difficult corrections when those distinct lines aren't so clear. This is using the frequency spectrum. And you can see the angles give you these nice peaks in the intensity, which relates to the velocity. So when you get a lot of wave noise, where there aren't traces, you're able to pick up that peak using this analysis, and it avoids subjectivity of people trying to interpret the lines themselves. Gives you a more solid base to work from. Again, this is what the automated Fourier analysis is identifying as that peak, but again, it provides you with a manual ability, if you're again not happy with that, to pick out that peak intensity in the spectrum. And again, you can apply that result, or you can choose to ignore it. So you can see here, this one's starting to get a little bit difficult. So again, you're able to use this to identify those peak flows, which you can adjust yourself. So that's a fixed measurement setting. If we wanted then to do batch processing, say we had another 50 videos, you would then save this and you would go up here to do batch processing. And that would open up another window which would allow you to load in the next 50 videos, and then you could cut and paste the water levels in, hit go, and it'll go through and process all of those. Each file is individually saved, so you can double click on it and it will bring you back into the software so you can manually check it. There's also a report function that you can export from here, which again contains all the information that you can see in this window in terms of geometric correction, discharge analyses. Everything's all contained in there, so then there's a little PDF format that can be printed out and filed away. So I'm now going to open up a new project to save. So I'm just going to take you now and we're going to load up a drone measurement. So typically with drone measurements in this type of view, as you can see here, not a lot of traces and a lot of wavy noise, so not as clear cut an analyses. Sometimes that oblique view helps improve the analyses looking across sunshine, and those waves are easy to track, but generally you can just see a tracer moving along there at the moment. So, and this is where STIV is good in these low tracer environments, and using every single frame, high resolution also helps with this. But again, when multiple drone measurements can be processed, this line distribution can be left the same, so the users aren't playing with many variables and less areas to introduce uncertainty. So with the drone videos, we go to pixel scanning, and we'll come back. So we've got a couple of options. If you know what the pixel scanning is already, you can just enter that value directly, or you can choose to specify 2 distance points. This is what I was talking about in regards to using a rangefinder and measuring a known distance. So we shall select, it brings up the window, so we can choose to say, well, I shot with a rangefinder across there, and again you've got the distance here. You can enter your distance in if you know it, and that will rectify the imagery and scale the pixels. You'll notice here that there's 2 cones here as well, so that's another option that you could use. We measured distance between those. It will completely serve the same purpose. So once again, enter your water level for the measurement. That will rectify it, and because the drone's looking straight down, you can see that the geometrically corrected image is exactly the same as the original image, unlike with a fixed camera with the oblique view. So, so our pixels are now scaled, they're all equally scaled across the image. We'll move on to our cross section, and it's just the same as with the cameras. You can, as I say, import that in a CSV file. You can select, if you know the positions, or you can enter those, or again you can draw it on manually or place the cross section where you wish. So as I mentioned, I usually try and set the cross section, or at least cut it to the right size initially, so I know that my scaling and everything is good, so it should go from bank to bank. So come out of that and accept it. So cross sections there, and then once again we get to our search lines. Once again we set the length, so I'm going to make them shorter this time because I want to avoid these bushes as part of the automated analysis. Set 20. So again, they go across the imagery. Hit create. So it's going to create our to make our STIV files for the analysis. And then once again, we'll go with the same option to begin with. And we'll see with the lacquer traces now, a little bit of variation across the channel. But this is where the deep learning really can help with this analysis. This is using the artificial intelligence to look at that spectrum analysis. So it takes a little bit longer. You can just see it correcting those velocities here as it's going across, and getting rid of the noise and the bias to come through. And there's one there which it's failed on, number 18. So once again, you can go through the manual correction. We might go and look at number 18. You can see the tagline there. The tagline is not moving, so it just gives a straight line. So you can see that our actual distribution of velocities look like that. These are some wave noises in here. They typically look like a V-shaped chevron. And again, so we're able to correct those and apply. If we go through, so this is what I mean by lacquer traces. You start getting a lot of these gravity wave noises in here. Find a nice one. Pretty good. So typically they give this V shape. So this is the peak, the trough, and the actual velocity that we're looking for is when you split those in half. So sometimes the imagery can get very noisy with these waves, and the deep learning is doing a great job of fixing that up. Again, not a lot of traces, but a lot of waves and turbulence within that, a lot of these V-shaped patterns. So again, the angle that you're looking for is through there. If we go back to the start, I'll just show you quickly the manual mode. So again, this is just placing the velocities as you see fit within the imagery, not related to a cross-section or discharge. Same process of rectifying the imagery. So with our search lines here, so we're going to be drawing these on manually, and as I said earlier, you can do this with a cross-section as well, but as you can see with our number of lines up here, 5, the interval distance between them, 2 meters. So what we can do is, we can hold and draw those in the area that we so wish. So we could draw some shorter ones there. You can choose the length. If you want to look down a reach, you can do something similar to that. Just as an example, so when you're happy, you can tick those. Again, make the STI. And then once again, run the analysis. This time it's just going to give you a long list of those velocity points. As it goes through, you can see a bit of an error there. So you can see there, quite nicely done. Sitting a bit on top of each other there, but you get the general idea that you're able to do that velocity analysis in different areas. The other nice thing about STIV that we've found, especially with drones, is that you are able to measure velocities between trees. So if I just come back to these search lines, edit, I'm just going to clear all of those search lines. I'm just going to move that to, say, 2. So if you had a very narrow area with your drone, So you want to get some analysis through there. Just allows you to get much closer to the banks or obstructions. Sometimes it upsets the automated analysis, but you can manually get in and correct these velocities. We'll just go over the quicker option this time. So you can see we've got two velocities there, 0.2, 0.17 between the trees. If we look at the STI analysis, so these lines here are the trees. Obviously they're not moving, so they represent straight lines. And you can see the traces here going between the flow with some waves there. So enables more functionality, something that it's very difficult to do with PIV analysis. Let's move to the next one. So again, you're picking up those velocities through obstructions. See the field of view. So, yeah, that is Hydro-STIV software. Thank you for your time. And yeah, if anybody would like any further information on Hydro-STIV or any other further information on the work that we've done with image spectrometry, my email contact details are there, so please drop me a line. Yeah, and thanks for listening. Cheers.